Hello everyone, this is the video for section 9.1 and this is the set of examples associated with this section. So we just got done talking about how different graphs look now from 2 dimensions to 3 dimensions. We've learned so much about two-dimensional mathematics in our last X amount of years, and now what we're doing is we're moving into the world of space, which again I think is going to open your eyes to the fact that there is a lot more math that we have not studied yet. So, this is a little statement at the top here that kind of reiterates what I was just talking about in the introduction video. But equations in 3 dimensions describe a surface, and a plane is an example of a really simple surface, where the equation in 2 dimensions describes a curve. Now remember, a curve is just a general term. It could be a line. So that line that we were talking about, that y equals 5 or z equals 3 or whatever, the line that we were talking about in 2 dimensions in the introduction, that line in space is going to be a surface, which happened to be a plane. Okay, so let's talk about example one and just think about what this stuff looks like. Now, if we were to take just the x squared plus y squared equals 1, and if we were to analyze this just in 2 dimensions, okay, what is that? Well, that's going to be a circle centered at the origin with a radius of 1, okay? Now, z equals 3, okay, we got to look past that for a minute because we never dealt with that in prior math classes because we only did x and y. But if we were just to look at x squared plus y squared equals 1, just that in 2 dimensions, we get a circle. What if we looked at it in 3 dimensions? Well, in 3 dimensions, we have, let me see if I can draw this. We have a cylinder. Now, why is that? Well, let's say we have the circle right there. Well, we could project the circle both vertically in the direction of positive z and in the direction of negative z, and what we get is this infinite cylinder. And remember, I said I can't draw, so what I've done for you is I've pulled out one of our fancy apps here. This is an app called Quick Graph Plus, and Quick Graph is an app that's free. It only does two-dimensional graphing, but Quick Graph Plus is a paid app, and I've always worked with the high school to buy this app for you all, so you can have it on your iPads and utilize it. I don't know when it's going to be available. So by the time you watch this video, we might have it. I don't know, but as soon as we get it, I will let you know and I will show you how to use it. Okay? But it's a great little app. You can take this, I can't show you on this video, but you can take this and spin it around and take a look at it and kind of analyze it and stretch it and shrink it and all sorts of things. But this is the equation x squared plus y squared is equal to 1. And if you look at the dimensions of it, you can see that it has a radius of 1. It's centered at the axis z, and it goes infinitely. And I know it looks like it's cut off, but that's just because when I took the picture of it, I shrunk it down so you could have a nice view of it. But it goes infinitely. There's no restriction to this. Okay? Now let's go back to our problem for a minute. So the question is, which points satisfy, satisfy both of these equations? So we're not looking at necessarily the, the x squared plus y squared equals 1 only, or just the z equals 3 only. We're trying to combine them together. Okay. So which points? Well, let's just say the points x, y, and z lie on the horizontal plane, z equals 3, and lie on the circle. Now, I'll talk about this in a second. Lie on the circle with radius 1, which is centered on the z-axis. Okay, now could you say this differently and be fine? Of course. This is just one way to say it. So what we're saying is that there is this plane z equals 3, which again we're getting here. We're calling it a horizontal. excuse me, horizontal plane because we're just thinking of it as the z-axis is up and down vertically. So it would be a horizontal plane based on that orientation. Um, and they lie in the circle. Now, why didn't we say cylinder? Well, the reason we didn't say cylinder is because we're restricting the cylinder where z is only equal to 3. So the cylinder is no longer infinite when we combine these together. The cylinder is going to be stuck at z equals 3. So z has to be equal to 3, and the cylinder then is stuck at a basically this circle in space. I'm going to go back to my computer generated drawing here. So you know what? I don't even have z equals 3 on here. Let's just pretend with me for a moment this is 3. What would happen then is if you took a plane and intersected it with the cylinder, you would get this simple ring right here. That's what we're talking about. So the points will be on that particular circle in space where z is always 3. So those are the points that are satisfied by these equations. Now, with example 2, we basically kind of answered it as we built our answer for example 1. So if we were to answer 2, I'd say this is a cylinder with a radius of 1 whose axis is the z-axis, something like that, okay? And then we'll talk about, okay, well then what if we took this and we made it an inequality? Let's say we made that less than 1 or equal to 1. Well, then now this is a cylinder, still has a radius of 1, still centered around that z-axis, but now it's solid. Now it's completely filled in. It's not hollow anymore. Okay, let's try example 3. Describe and sketch the surface in 3 dimensions represented by y equals x. I'm not going to sketch it because it's not going to go well, but let's just think about what this means, okay? So we have our x and y axes, and this is the simple line that we have been graphing for probably many years, since about pre-algebra-ish. There you go, that's the y equals x line, one of the ones we use all the time. What does that look like in space? Well, it's going to be a plane. That plane is going to be associated with that line, but z can be anything. So keep in mind, like I've told you already before in this section, where is z? Well, z is not defined. Therefore, z can be anything. Same idea as in example 2. Where is z? Z isn't defined. It can be anything. Okay, where is the picture? Well, it looks something like that. And again, I wish I could twist and turn this for you. I wish you had this on your device that you could twist and turn, and hopefully soon. But there's the plane. If you can kind of visualize it, it cuts through the XY plane, sort of at this angle that we know it does, and then it just goes forever in the z direction, up and down. All right, let's talk about your first formula. So one of the things about this course that is very different, I think, to other AP calculus classes is that there are many, many, many formulas. You will have formulas with every unit. On your exams, I will allow you to use sort of a note card like sheet where I want you to start building a nice condensed formula sheet. And what that will do is it will help you organize your thoughts. It will help you be able to find your formulas quickly and then understand kind of when and where you want to use those. So please begin that now. If you have a note card at home, you can certainly do that. You can also use just a blank piece of paper. Obviously, is fine. You can use your iPad, blank page or whatever. Just what I want you to do is keep in mind that this is supposed to be nice and condensed and easy to find and read and use. Okay, so the distance formula is one that is very easy, and you've probably seen this a number of times in the past. And so if you want this on there, put it on there. But if you don't and you feel like you haven't memorized and it's really no big deal, then that's fine as well. Okay, so it's totally up to you. I'm just telling you this is kind of your first formula here. All right, one thing in our textbook. So our textbook is written by James Stewart, and he and many people for that matter, they use distance and the notation for distance as what looks sort of like the absolute value bars. Okay, now that's totally fine. A lot of people have done that. A lot of the material that we use in our class will do that. I often will write this as the magnitude, which can be double bars, not single bars. So just keep in mind that when you see magnitude or distance, you may see it as a single bar, like absolute value. You may see it like a double bar, okay? But it really has the same meaning. It depends on the type of text, depends on the university, it depends on all sorts of things, okay? All right, so here is the distance formula between 2 points. And over in our picture here, they're going to go from P1 to P2. Now, another thing about this course that's a little bit different is that I will be going through proofs with you all throughout the course. Now, this is not a proof-based multivariable class though. So if you really like proofs, you'll be disappointed. If you really dislike proofs, you'll be very happy, okay? This is, again, concurrent enrollment with Normandale. Therefore, we follow sort of their progression here. And there are proofs that I'm going to provide, proofs that we're going to go through, but it's not a heavily proof-based class. I will not be testing you on a lot of proofs, but I do want you to be aware of how to go through a proof. Now, this is a really easy proof, okay? So what I'm going to do is I'm going to go in our little diagram here, and we're going to draw out a couple things. So the first thing we're going to do is we're going to go from P1 to B, and then we're also going to go look at P1 and A and B, this little triangle right here, okay? And I'm going to use Pythagorean theorem to write the distance as the distance from P1 to B, so the hypotenuse, squared, equal to A to P1 squared, so one leg, plus A to B squared, so the other leg. All right, so then what I'm going to do is I'm going to look at another triangle here. So we're going to look at the triangle P1 to P2 and P2 to B, and then P1 to B. So we're going to look at this triangle over here. So what we're doing is just breaking this all down into space. And we're going to use the Pythagorean theorem. We have P1 to P2 squared, and then we have P2 to B squared and P1 to B squared. So two little triangles, Pythagorean theorem for both. So now if you notice, we have the distance from P1 to B is written in both. So what we'll do is take the stuff here in blue, so the distance from A to P1 squared plus from A to B squared, we're going to substitute that in here for P1 to B. So we have this new equation that looks something like this. All of this we're going to leave, okay? And then we're going to add the distance from A to P1 and then A to B, like that. And then what we'll do is we'll rewrite this. So first off, let's go back up to the top. What are we trying to find? Well, we're trying to find the distance from P1 to B to P2. Okay, so let's take the square root of this left side. That's the distance we're trying to shoot for, which means that we got to take the square root of this side. And if we look at P2 and B, so we look over here, P2 and B, we're going to subtract the different elements. However, the x value and the y value are identical in both. So really, the distance between P2 and B is simply just Z2 minus Z1. So we have Z2 minus Z1, and we're squaring that. Then we have from A to P1. So A to P1, well, okay, The only thing that differs is x. Y is the same, z is the same. So what we have there is x2 minus x1, and we're squaring that. Plus the very last one, we have a to b. Again, x doesn't change, y changes, and z does not change. So we simply have y2 minus y1, and we square it. And again, you can arrange it a little bit, and you will have your distance formula. So really easy proof, kind of a fun one. You most likely have seen that in the past, but I like to show that one just because it's a nice little intro proof. Okay, we're going to move on to the next page. Okay, we're going to start with example 4. We're just going to use the distance formula between P and Q. And so what we'll do is we'll calculate by taking the square root of, and you can do this in any order you want. I usually do the z's first. So you take z2 minus z1 squared plus y2 minus y1 squared, and then x2 minus x1 squared. And then we're just going to simplify this down. So we get the square root of 2 squared, which is 4, plus negative 2 squared, which is 4, plus 1 squared, which is 1. And we get the square root of 9, which is going to give us a distance of 3. So there you go. Distance formula, nice and easy. All right, let's do a sphere. So you need to know the formula for a sphere. You probably have seen it before. I certainly hope so. If not, you can certainly write it down on your note card or your piece of paper that you're sort of organizing these formulas on. I'll show you how to come up with an equation of a sphere if you have sort of a jumbled mess and it doesn't quite look like the formula that we're shooting for. If you remember back to higher algebra, you did something called completing the square, and that's what the technique we're going to use here. First thing is that we want to group everything together that's of similar terms. So we're going to take the x squared and the 4x, put those together. We got y squared minus 6y, and then z squared plus 2z, and we still have that plus 6, it's equal to 0. And then we're going to complete the squares. So we have x squared plus 4x. We really want that to be x squared plus 4x plus 4 because that's a perfect square trinomial. Then we have, and by the way, if you forgot that technique, what you're doing mathematically is you're taking the middle term, dividing it by 2, and then squaring it. So 4 divided by 2 is 2, squared is 4. Y squared minus 6y, if we divide negative 6 by 2, you get negative 3 squared is 9. So that's going to be 9 there. And then z squared plus 2z. 2 divided by 2 is 1, squared is 1. Now we have the plus 6, but we also added all this other stuff. So what we need to do is subtract 4 here, and subtract 9, and subtract 1, because again, we need to make sure the equation hasn't changed. We're just adjusting the way it looks. Okay, here's the whole reason why we did that. If we take x squared plus 4x plus 4, so we take this perfect square trinomial, we can write that as x plus 2 squared, which is exactly the goal. And if you look up in our equation for a sphere, that's the setup that we're looking for. For y, we have y minus 3 squared. And by the way, this, if you aren't picking up the pattern, half of this middle term is what goes here, the perfect square trinomial, okay? Then we have z plus 1 squared. And then all of the stuff over here will combine. Let's see, we're going to have 8. So we're going to have negative 8. So that means we add it over, and we get 8. And so what we've done is we've set up sort of the generic or general equation of a sphere. This means that what we have is a center at negative 2, 3, and negative 1. That's gonna occur based on what we've separated with our set up with our perfect square trinomials, and then the radius will be the square root of 8. or the same thing as 2 root 2. So there you go, just a nice little skill. Again, you've probably practiced it as you prepped for the ACT and or maybe other classes, I'm not sure. Last thing, as we work through all of our notes this year, the hope is that we'll have all of our answers. That's just good for everybody. Me, you, doesn't matter. We're working through them. We can check our work, make sure that we're accurate. Or I might skip something and say, you know what, why don't you try that one on your own, and then you can go check the answer, that kind of thing. Okay? All right, that is section 9.1. Thank you.